All right, introduction to online machine learning algorithms. Hopefully everyone's in the right room. I use lots of memes and animated GIFs, and they're mainly, I take pictures of that. Thanks. They're mainly, I didn't have any IP, so if anybody wants to steal all my ideas and use them, I can't really stop them from doing that. That doesn't seem fair. Introduction, what just happened? Okay, a little about me. Trevor Grant, I'm an open source evangelist at IBM. I am a PMC on the Apache Mahout project, PPMC on Apache Streams Incubating. I blog, I have degrees, I went to school, I'm on Twitter. And that's important. How many people use Twitter? Some tweeters in here? Okay, this is going to be a very interactive session. I would like everyone to get out your Twitter app and be advised, Rockin' Trevo is me, but more importantly for the excitingness of this whole talk, if you could tweet things at Trevo Live, and that's going to be on the top corner of every slide, so you don't have to remember it. Speaking of which, because I need to make sure I have enough content to make all this work, is anybody opposed to me taking a picture, a very blurry Twitter picture of them? Okay, cool. 1 second, and okay. So yeah, that's, while I do this, let's talk about what we're going to talk about. This is a real-time talk. I thought it was very fun to do that in the theme of everything that's going to be happening here. Sorry, I'm messing with my phone. This is the first time I've ever tried to live tweet my own talk, so. Yeah, we're doing everything live, real-time, and streaming. And as the keynote this morning said, big data is truly going mainstream, and I tend to agree with that. If you have ever seen me talk before, can infer from all my tattoos and wearing the wrong conference shirt, I don't like stuff that's mainstream. Big data, too mainstream. Everyone's doing big data now. That's not very exciting. If everyone's doing it, then how are we going to be coming up with cool new things that everyone's talking about? So, streaming machine online learning, you've probably never heard of it because that's the cool thing that no one's doing yet. The fact that you're sitting in this room means you're at least interested in it and understand that it is the cool new thing. If everybody else is doing machine learning on big data, what's the next thing? Streaming data. And we need to do then really it should be artificial intelligence is our new buzzword. We don't call it machine learning anymore. That's also too mainstream. This is the Hipster Trap, and what PBRs, American Spirits, and an old Nokia camera are to hipsters. For us big data hipsters, it's online, real-time, GPU-accelerated, machine learning, artificial intelligence, blah, blah, blah. So, I already talked about this. We're going to be doing live tweeting. Please, please do. It is important to me because I'm very vain, but also for a little demo we're going to have later. But let's get into the talk then. Buzzwords. There are a lot of buzzwords floating around. There's been some talks on online streaming algorithms at this conference. If you've been on the circuit all spring, you've probably heard a lot of it. Everyone's talking about doing machine learning in real time, machine learning online algorithms versus offline, lambda machine learning architecture, kappa architectures, statistical models, adversarial models, and blah, 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 blah. So this talk is going to be about disambiguating a lot of these buzzwords. And hopefully what you're going to get out of that then is when you hear people rattling these things off, you don't think, oh man, that sounds like so cool, that's so hard. Just like machine learning is statistics at the end of the day, but maybe it's a little spooky, ooh, black magic-y statistics. Yeah, but it's just statistics. And artificial intelligence is just even more, ooh, dressed up machine learning. The same way, we're going to try to disambiguate all these things with the online and the real time and the offline. So, starting, first buzzword we're going to disambiguate. Online machine learning versus offline machine learning. Online, all that means is for every piece of record you receive, you're doing something with it. You're processing it, you are making either a prediction with it, you are updating your parameter space from it. Batch, offline is basically your batch. That's it. It doesn't necessarily mean it's a smart or really intelligent online algorithm. It doesn't mean that it's not. It just means you're doing something for every event that we get, or for every event we receive. In graphics forms, I know that, I guess not everyone, this may be a somewhat culturally relevant joke. What they're doing there is something we call a keg stand, and you drink beer straight out of the hose. This is online processing of beer. This is batch processing of liquor. You just chug yourself a whole bottle of Jack Daniels. Illustrative of online versus offline processing, kind of. Just because something is offline doesn't mean it's slow, and just because something is online doesn't mean it's fast. And my sort of anecdotal example of this would be, imagine two stock traders. We've got a broker who sits out in Des Moines, Iowa. He's not next to the exchanges. At the end of the day, this is an old-timey broker too. Doesn't even have internet. End of the day, they get a FTP upload, or he gets it of all the new prices. As soon as he gets the prices, he puts his new orders in, fires them off, calls it in. That's, for our definitions, that's online. He got information and instantly made an action on it. The contra to that is consider a high-frequency trading. You know, those guys who are like burning on like algorithms onto silicone, and they are batching data on a 15 millisecond batches and then executing orders on that. Well, they're batching their data. They're not taking every tick that comes in and working on it. That would be an offline algorithm. This is a sort of contrived and extreme example, but again, just trying to drive the point home that just because we're doing online learning or an online algorithm doesn't mean we're super fast. And it also kind of depends on your architecture. In the case of the stockbroker, yeah, there's online things happening upstream, but from his perspective, he's doing something as soon as he gets the data. Thus, yeah, this is a slow online. It's a sloth. He slowly looks at his celery and says, nope. And this is a hamster. He jams all these carrots in his mouth, but then he just keeps them in his mouth. He'll eat them later. So, Lambda versus Kappa architecture. How many people are familiar in just the general space of Lambda architecture and Kappa architecture? The words, okay, we got, okay. I'm not gonna even super dive into that. I'm gonna just keep it, because it's not all the hands. But for the purposes of machine learning, we think of a Lambda architecture is we do all our training in an offline sense, and we make all our predictions online, if you track me. Versus a Kappa architecture, we're both making predictions and updating our parameter space for every record that comes in. So the idea, like, of a Lambda architecture, you had a bunch of historical data, you trained a model in batch, like in Spark, and then you loaded it up as like a microservice to make predictions in your real-time stream. And then whereas a Kappa would be simultaneously updating the parameter space of the model and also making predictions with those updated parameters. We'll have a little bit more illustrative example if that doesn't 100% make sense. Lambdas, the big problem with them is they can't handle novel information. Because you train that offline model in on a set of data, imagine like a rectangular of data, you had 15 columns of a linear model. If you now all of a sudden have a 16th column, new data is coming in, or a category, a new category of data, the model's only been trained to recognize 5 categories, it can't update itself. That's just part of the lambda-ness of them. Whereas a Kappa can, I'm not even sure what the relevance there was. I thought it was funny a couple minutes ago. A Kappa model, good case, let's say we were doing some sort of like language processing and new words come in. In a Lambda model, you've got new words coming in your DFIDF. You didn't train on those, it can't handle that. But since with a Kappa model, you're updating your parameter space with every new record, then it can handle new words. And it doesn't necessarily, again, mean one's better or the other. It depends on what you're trying to do and what you're trying to get out of it. So, because people like love saying, ooh, Kappa architecture, Kappa architecture, Kappa architecture. Yeah, okay, we'll do.
So with Kappa architecture, every time a new snake drops into the pit, Indiana Jones can realize that it's different and put down a new torch.
That would work. I think it was because all of a sudden he was in a pit of snakes, and that's an entire new situation. But oh, now that I think about it, I want to just, since we've taken a little pause, I want to remember everyone to please get out your cell phones and tweet at #TrevoLive. Thank you. Statistical versus adversarial. This is a fun new kind of field that's coming about that's required by streaming algorithms. Statistical models, I'm going to imagine mainly data scientists in here, based on the title. That's probably who I attracted in this. So you're familiar with your common statistical methods. You've got confusion matrices, R-squared, mean squared errors, area under curve, blah, blah, blah. Adversarial models arise because consider a model coming in and you're making a prediction and you're trying to learn in real time. And then the question is, if you are making a prediction, you probably don't have the answer. So how are you training anything in real time? And so adversarial models gets into, and you have an environment that changes on you. So case in point, spammers and hackers. This is where a lot of these things were a lot of the groundbreaking work on this was done. If you think of spammers, and you've got a spam detection algorithm on your email, well, as your spam detection filters get more sophisticated, spammers are changing their strategies. So they're constant. It's like a constant, war between the algorithm and nature. And so we grade these. What we end up having to use is some new sets of tools we can use. We'll get into, but looking at like A/B testing, multi-arm bandits, adversarial models. We'll come back to those in a minute. So then my last, I think, buzzword, yes, is the granddaddy of all buzzwords, real time. Real time is a really safe buzzword if you feel like your product or thing that you just made needs another buzzword. Generally, as best I can tell, it means at least as fast as everyone else is doing it. When I was in my first job, I worked in media strategy. People would get a report last week and then would take that report and have a meeting about it. And then the next day, they would get around to putting some updates to like an online campaign in, and then the whole process would repeat once a week. So like with at least a week lag, but they called it, yeah, that's real-time adjustments we were making to the campaign because they weren't waiting till the campaign was totally done to make the adjustments. Okay. I used to work at Jimmy John's. If anybody's familiar with Jimmy John's, they have subs so fast you'll freak. That was real-time sandwich delivery. It's totally industry, whatever. You can't get in trouble if you call your algorithm real-time, more or less. All right, so now we'll get into some basic online algorithms. First one will be k-means. I stole this graphic, but this one in particularly, I do have a really nice photo credit on, and you should go check that out. It's a really good blog post that talks about how all these work if you want to dive a little deeper into the k-means algorithm. We are intro to online machine learning, so we're just going to talk it through real quick. Imagine you initialize with these 4 centers, cluster centers. You get a new point in, it measures, okay, it's closest to the red one, and if it's red, then that means that the average center of all the reds needs to move a little closer to that new point. This is a gross oversimplification. Again, please read a blog, but that's the idea. A new point comes in, we make a prediction, we update our parameter space. Linear regression online. Again, great blog about it, go check those guys out, but we had an original fit line. We got a new point. Okay, that's the line between those, some sort of weighted average. We change the slope of our line, we have a new line. We get another new point. We draw a new line, we slightly update the line. Again, this isn't to scale at all, but that's the gist of how one point at a time we're updating our parameter space. Deep learning, without going into all the magic of neural networks, this can also work with deep learning because for every point you get, you can backpropagate on a point-by-point basis. Backpropagation is how we solve for neural networks. If you know what I'm talking about, then that'll make sense, and if you don't, there's a really good book or online thing I can tell you about how to learn neural networks. and I will tell you after class. So when do we actually end up using online algorithms? Most of the cases at the moment are, time check, not bad. Most of the cases online at the moment are around anomaly detection, detecting anomalies. And that's why we want to do online, because the state of the world can change. The state of the underlying world changes, and we want to update our parameter space. So challenges and solutions of online. Again, I hinted at this earlier, but why would you be predicting an answer if you already knew it? So there's a latency usually between the time we know what our answers are. And that's where a lot of these onlines. If there is no reasonable way to do that, then don't try to update your parameter space. Like if you make a prediction like a recommendation, the user either accepts or rejects your recommendation and then goes on. But if it's going to be like a week before you get the real answers, maybe online learning isn't the thing you need. Maybe that's fine to use a batch. Normal problems that you have with latency in streaming engines is that you can overload your hardware. And throwing machine learning algorithms on top of a streaming engine is going to add a significant load to your hardware. Adversarial analysis, you can grade how the online algorithm's doing against an offline companion that has access to a full set of data and like what sort of degradation you're seeing. A/B testing, A/B testing is you've got two algorithms in flight. You see how you're randomly assigning new things coming into one or the other, and looking at how the one algorithm performs against the other in real time. Multi-arm bandits, very similar to A/B testing. The difference is maybe you're doing your A/B testing on like 10% of all the stuff coming through, and the other 90% are constantly being served with whoever's doing the best in the A/B test. So again, short version, all things worth looking more into. But the reason that all these are necessary is your algorithm in an online streaming context is an actor in the environment in which it's operating. It rewrites history. Because your algorithm was out there doing things, your algorithm made a recommendation and the people either used it or they didn't. There's no way to go back and like back test that. It changed history, your algorithm. So it's not like the more traditional like, oh, we can back test this, we'll try the model this way, we'll try the model that way. Backtesting an algorithm, you can't backtest an algorithm for these onlines. It's like trying to say, well, what if like backtesting a game of chess. If you made one different move, the entire rest of the game would have gone totally differently. So it's difficult to apply a lot of these old techniques to backtesting. And you never can know what would have happened had you made other recommendations. Yodo is you only die once, but the point is your algorithm made a choice and it has to stick with it, and we'll never know what could have been. It's some really, really deep stuff for our online algorithms. So I got what, 10 minutes? Oh, okay. Oh, all right, it's 20 minutes. Is that what I got? Round. At any rate. I wasn't managing my clock right, but we're going to do okay. Cognitive AI. I loved it today in the Teradata keynote. Finally didn't admit, but made the point that recommenders are AI. But nobody's been wanting to say that because AI is this spooky and magical thing, and recommenders are old, boring e-commerce stuff, and we're not excited about those. But he called it out. He's like, oh yeah, recommenders, it's AI. And I'm like, yes, it is. So enter the Apache Mahout project. Again, PMC for Apache Mahout. People who've heard of Mahout. Keep those hands up if you think Mahout is machine learning on MapReduce. Okay, good. Then our marketing campaigns are working because Apache Mahout is now an engine-neutral machine learning that runs on Flink, Spark, various other underlying distributed systems. So, and as we will very quickly, it also maintains a strong legacy of having some really first-class, best-in-class for open source recommender engines. In this case, we're going to talk about briefly the correlated co-occurrence recommender. It's a collaborative filtering style recommender, and it's behavior-based, like ALS. The difference is ALS is what we call single modal. When you're doing an ALS recommender, you get basically one action, like ratings. Think of the Netflix version. You want to recommend something based on the ratings that other people have made. That's great, but that throws away a lot of behavior, like information about the person, their fast viewing history, past purchase history, abandoned carts. So much information gets thrown out the door when we use a single motor recommender like ALS. That's a simple co-occurrence matrix. You take action and users, transpose times self, and their history. Correlated co-occurrence matrix it kind of expands that out. Again, these are exciting things, but what we want to get into is our actual version of what happened. So in here, what we're doing is I got a bunch of historical tweets about pizza, ran them into Spark. This is a lambda style because I calculated all of my matrices. If you look at these matrices, calculated all those in Spark, took the co-occurrence matrices, uploaded them into a Flink job, hooked Flink up to the live Twitter stream, and I'm using that, and then we're just making recommendations for every algorithm that comes in. Make sense? So Python did that, yeah, blah, blah, blah. The code's all up in GitHub. Calculated those. Flink code's up in GitHub too. Cool. More importantly, all right, who's been following directions and live tweeting? I got one, but that's okay, that's enough. All right, I'm very disappointed. Hold up. Now, this data was actually trained on, oh man. Give me 1 second. See if we can just, I've lost my mic altogether. There it is. Nope, that's all I needed to do. All right. I couldn't find my map. It turns the resolution like crazy high up on this one. Okay, so what this whole thing is doing is it takes a tweet in and it recommends hashtags based on pizza tweets. Can somebody read those who's sitting up close? Yeah. No, just tell me what they are. I can't see it. All right, well, from whatever data set of tweets about pizza that I started with, whatever crowd is looking good for DataWorks Summit Travel Live, that's my own tweet. I don't think anybody tweeted anything. That was my shameless, well, I'm glad I made one. So that's what it's doing. Is there? Yeah. Okay, well then it's entirely possible that it's, yeah, right? Oh, there they are. Okay, no, I see them now. I didn't scroll down enough. You're right. Okay, thank you everyone for doing that. All right, cool. Well, I'm already switched back over. No, probably this one's dead. Okay, I'm gonna land this plane at any rate if I can get everything going again. Of course. Lost that. That makes sense. Go back into present mode. Nice. All right. So these are what the tweets end up looking like. And we have now created a cognitive AI, hybrid Lambda architecture, online recommenders, GPU accelerated, adversarial, and I don't think there was any adversaries in there, but it's still a cool buzzword. It's also very real time. The difference then, all right, so what I just showed you, the machine learning was happening actually in the stream. This is, in general, fallen out of favor as an architecture. What we normally are seeing anymore is microservice architecture. Same general idea, we calculate offline, but then Flink, instead of actually doing the tweets inside Flink, is firing off to a microservice that is for every tweet that comes in. Same general idea. This is, the advantage of this is it makes it a lot easier to hot swap your parameters as you're going along. So when you hear people talking about microservice architectures, that's basically all they're doing. If it were a Kappa architecture, then it would be same general idea. We could do like a machine, like a deep learning net, like an autoencoder, and the idea would be, how many people are familiar with an autoencoder? About 2? Okay, so the gist of it is it's a neural network that takes itself as like a tweet is, let's say, as an input, and then tries to predict the tweet. And if then the tweet is something too weird, the idea is it's going to have a lot of error on making its own prediction. It can predict things that it's used to seeing. In this case, then, it would say, hey, there's something weird about this tweet. Maybe the person's drunk or whatever, or shouldn't be tweeting. So, and it fires something back. It says, are you sure you want to tweet that? And it would be a handy Twitter functionality. So, in conclusion, landing this whole thing, we've done a lot of buzzwords, we told some jokes, we had a lot of fun, we did some tweeting, it was interactive. In general, that there's nothing special about all of these buzzwords, because that's what they are, they're buzzwords. And don't get overly impressed if you hear someone come in and telling them to you. Final thoughts, yeah, either don't get overwhelmed by people calling or using their buzzwords, or if you want to make your service sound more impressive, now you know the proper way to use all these buzzwords so you can dance around and not be technically lying. So best of luck to you on that, good or evil, however you decide to go. This is a conference, and every other conference I've ever been to in Silicon Valley really is just a bunch of unsolicited sales pitches, and I'd feel weird if I didn't make a few. First one, Software Freedom Conservancy is a non-for-profit that defends open source software and license and copyrights. Check them out, support them. The Chicago Vets Club, I'm a veteran, and this is something I really believe in. It's helping other vets get into tech. If you know any vets or anyone in the Chicagoland area, make sure to tweet at them that this is a cool resource. And the 10th Annual Biostats Ecology Education and Research Conference at my alma mater, Illinois State University, will be happening this year, October 6th through 8th. So everyone make sure to check that out and put in for funding now. And with that, I end this presentation with questions. Questions? Joe.
Isn't it possible? Is this on? Yep. Is it possible to take an online stream and replay it back? You said when your chess game analogy, you said you lose history. Can't you just replay the stream back?
The problem with replaying the stream back, depending on exactly what you were doing, is let's again think of the recommender example. You know, you made recommendations to a bunch of people and they went and created actions. But what would have happened if you made totally different recommendations? There's no way to know what that person would have done. You can replay the stream, but it's not necessarily going to be really informative. All you're doing is testing the technical efficiency that your network is doing what you think it's going to do. So that's why we would have an A/B test going where you're trying, one recommendation algorithm versus another recommendation algorithm and seeing which one has higher conversion rates, for example, to the primary action would be the idea there. And that's the only really legit way to test it because you didn't change history. 10 minutes? Okay.
So,
oh, wait. Sorry.
Okay, so I'm also interested in helping people learn sort of entry-level concepts, and but I'm new to this, so I'm learning a lot. Thank you. When it comes to something like data entry, and you want to autocomplete, so you want to take a look at what past data has been put into that field.
Yes.
And then try to recommend as people type, oh, it looks like you type in this word, which, by the way, is excellent for things like making sure that your data is clean, because you can recommend the same canonical word that other people are typing, right? And you catch mistakes, all that kind of stuff. Anyway, In the scenario where you're pretty much sure that there's a limited set of data that people are going to type, so it's not changing often, then I've seen scenarios where you can just use databases to do that. It's kind of clunky, but it works.
Yep.
I was just wondering, is there like a, how would you recommend somebody solve that kind of problem versus I have no idea what people are going to be typing into that box because it's what they might type is constantly changing, but you still want to make a recommendation.
Yep.
So one's changing, one's not changing. What would you recommend in that scenario?
My answer is going to be partly based on the fact, again, I love Mahout, and that's my hammer,
That's
so
fine.
everything turns into a nail.
Yeah, that's fine.
But at least it is a scalable answer. And you're going to, once again, you're going to create a recommendation matrix that starts with, your primary action is the combination of letters you've typed in so far.
Right.
You've got recommendations that come out. To make it scalable, you index the whole thing with Solr. And then you've got a REST API for free too. Then in the first case, the former case, you don't need to, you'll barely need to update. You're going to very carefully curate what the possible actions can be, which are the correct things that should be typed in. In the latter case, you're just going to be a lot looser with the training, and you'll maybe rerun that offline batch, that training, maybe nightly, maybe hourly, maybe monthly. It depends what kind of frequency you're seeing new things and you want to incorporate new things into your possible recommendation outcome set.
Yep, okay, that sounds good.
Cool. And yeah, it's very specific, so we can dive into some weeds afterwards. Please come. All right, well, that's it. Oh, whoa, we got one. Oh, the shameless, I guess I should have made a shameless plug for them too.
Could you repeat the question?
Sorry, the question was, what was the book that I was plugging that's good for deep learning? It's not letting me type on this. What's up?
Yeah.
For the neural network stuff, yeah. It's, hold up, let me see if I can, give me 1 hot minute since we're not coming in hot on questions. But this is a really, there we go. Let's see, I'm trying to, nope, missed. Why are you not, there we go. So that's the one, it should look like that. Now, well, now I can't see what it is, darn it. All right, hold up. Let me get back over here. Yeah, that's a good idea. Copy. Oh, there you go. I do love live tweeting, but it's a really long URL. It's neuralnetworksanddeeplearning.com, all one word. I don't know how to use these stupid Macs, but neuralnetworksanddeeplearning.com is what I would recommend. Like I said, it's like about 7 chapters. Really, it's a deep dive, but you really get into it and learn. If you look at the Mahout implementation, which is still a work in process, it pretty closely follows his notation too. So you can see it in like a coded up form in a mathematically expressive Scala in there. So, cool. All right. Oh, I guess we're done. Oh, we got 5 minutes. Well, whatever. I think we're good on questions. I appreciate y'all coming out, and have a good conference.